You did such a good job. That was awesome.
Thank you.
It's seriously like one of my favorite plays I've watched.
Yeah, which like I said, honestly, it allowed me to not worry and just go do that. It's hot though.
Yeah.
It's I think Simpson needs to create like Simpson needs to create like a pre-med. Because there was some, because for example, like, there's like some stuff that I only do because like I took immunology. Or that's where I remember. Microbiology.
Wow, that's exciting!
I know. I'm just glad we're done. Yeah. It went as well as it was going to go. It's no one really knows because I was the very first class. Like I was the very first exam of the new 25th of the new exam.
So you don't have a baseline.
So we have no idea. Which is nice. So I'm hoping that they set the curve based on my score.
Well, by definition, you're going to be the average.
Right? So we'll see. But I'm just glad we got to be done.
Well, good luck. Let me know how it turns out. I want to know how especially the physics scores.
Yes. Also, fluids. Dr. Olsgaard. Well, Dr. Olsgaard, yes, there was fluids.
There's definitely.
So, what can I tell you about what this was this summer? Because like, I really don't think that there will be much fluids on the MCAT, so you guys really want to go with fluids, or like, well, it's not really going to be on the MCAT. So.
Yeah, no, all of your circulatory system is based on fluids.
Yeah.
So it is important. Okay, so I want to go over, before doing anything else, I'm going to try to speak louder today because some of you guys are having difficulty hearing today. Fluids, schedule for the week. So today we'll pretty much finish up with new material. Tomorrow we're going to do like a mini version of a lab. I know not everybody can be here on the Tuesday. We're basically just going to make this like an extra credit lab. Anybody who can't come at the normal Tuesday time, but still wants to do the extra credit lab, just come see me and I can set up another time for you. Let's see. So Tuesday is going to be like a little mini lab, which will count as extra credit. Wednesday, we'll do our normal problem session for the homework that's due Friday. There is no quiz this week, because we want to spend all day Friday just going over and reviewing stuff that you'll need for the final. So again, today, new stuff. Tomorrow, mini lab. Wednesday, problem review. And Friday, our problem session Wednesday, and then review on Friday. Questions about scheduling? Okay, in that case, let's review from last time. So, Bohr had this model for the atom. And the model was based on a couple of experiments that we didn't really talk about. It was based on this Rutherford scattering, which you should have read about last weekend. But basically what Rutherford scattering did is it showed that there was an atomic nucleus. And before that, they didn't really know about protons and neutrons condensed into this compact, hard nucleus. So essentially what they did is they shot some radioactive particles at it, and what they found is that every once in a while the atom bounced, or the radioactive particle bounced back, which means it has to be bouncing off something. And the model at the time was that they knew electrons were fairly tiny, so that an atom they thought was kind of like a dense soup of positive charge. And if that's the case, then if you have this big radioactive particle coming in, it should just pass right through. But that was not the case. It ended up bouncing back, so they're like, there's got to be something that it's bouncing off of. The other thing that they found with that experiment is that the atom is like 99.9% empty. It's pretty much just empty space, except for this really, really tiny hard nucleus at the center. And using that information, Bohr was able to say, all right, well, we know about matter waves, we know about this quantization effect where the energy levels are quantized. I'm messing with my history here a little bit, but we'll make the physics easier to understand. So basically what the model showed is that if we assume some wavelength that has to match at the boundaries going around the circumference of the atom, then we can predict two things. We can predict the energy levels of the atom, which he showed was minus 13.6 electron volts, divided by n squared, where n was the energy level of the atom. It was just some integer level, some integer number. So you could have energy level 1, energy level 2, energy level 3, all indexed by that n. Bohr was also able to get a good estimate of the radius of the atom, 0.0529 nanometers. Again, this was also times n squared. I'm running out of room here. It's a little smaller. Times the n squared. So that's that energy level number, that what we call the principal quantum number, tells me both the energy of the electron in the atom and also the radius of the atom. And the interpretation is that if I look at those different energy level numbers, and of course, by that formula, I'm going to get a bigger atom for bigger quantum numbers n. And not only that, but we get to predict what color light is going to come out of individual atoms. And this is what the lab is going to be about tomorrow. So if I have an electron in the n equals 2 state, and it drops down, we know that it emits some photon of some color. The energy of that photon, we know from the photoelectric effect, is just given by a constant times the frequency. But that has to be equal to whatever energy the atom lost. So it's going to be equal to energy level 2 minus energy level 1, because the atom went from energy 2 to energy 1. Similarly, if we have a photon coming in, let's say, again, the atom starts in the n equals 2 state, a photon comes in, hits the electron in the atom, that atom can jump to the excited state. Again, my photon would start with an energy HF, but this time the energy would be equal to the difference between states 3 and 2. So and this is, fundamentally, this is how all atoms exchange energy. It's really just shooting photons back and forth at each other, and jumping back and forth between these different energy levels. Let's see. So we covered the Bohr atom last time. We also talked about the uncertainty principle. Which said, my position always has some uncertainty, my momentum always has some uncertainty to it. We know that just from lab, from experimental physics, that whenever you make a measurement of something, there's always some uncertainty associated with it. And what Heisenberg showed was that if I take the product of the uncertainty in the position and the uncertainty in the momentum, I've always got to get bigger than h over 4 pi. And we said that this was a fundamental relationship. This wasn't just a matter of us having bad measuring equipment. It's actually a fundamental relationship that has to deal with the fact that matter has a wave, has wave-like properties, and that the momentum depends on the wavelength. So if we're measuring the momentum, that means the atom has to have a well-defined wavelength. Because we said before that the momentum was just Planck's constant divided by the wavelength. So if I have a well-defined wavelength, that means it has to be spread out. And if it's spread out, then I can't know very well where the atom is. So that's where we got to last time. Let me stop there and take questions before we jump to new material. Any questions on what we covered last time?
I have a question.
Yeah.
So is the, what did you, I'll ask it later.
Okay. Other questions? Okay, so this model was actually very successful. It essentially, so I showed you the atomic lamp of before, and tomorrow we're going to look at hydrogen lamps and look at the different colors that come out of that. And that was a real mystery in the 1800s. Why is it that when I excite a pure atom, I get little bands of color? I don't just get like a continuous rainbow like I would do with a light bulb. I get these bands of color. Why do I only get certain bands of color? Why do I only get like a red line and then a green line and then maybe a purple line? And Bohr's model predicted those lines very, very precisely. But despite this, it wasn't correct. So if you do more experiments, what you find is if you look at those colored lines that we saw looking through the diffraction ratings before, it turns out there are other colored lines. Sometimes you'll get like a yellow line, and then there's another one that it looks like one yellow line, but if you look really closely, there's two yellow lines that are really, really close together. Other things is that the Bohr model didn't work for atoms that had more than one electron. It really only worked for hydrogen. So we want to, I've already covered
That
that.
was my question. So they know that it works for the hydrogen atom.
Yeah.
They tried to figure it out for any of the other ones.
Well, people have tried. So actually, I should make a correction to what I said. It works for the hydrogen and then hydrogen-like atoms.
Okay.
What I mean by hydrogen-like is if I take helium and then I take out one of the electrons, all I have to do, the model will still predict the lines correctly as long as I assume there's two protons in the nucleus. People have made other efforts to describe what happens when you have more than one electron. People spend a lot of time doing that. The problem is that you run into something called the many-body problem. So it turns out that physics problems are really easy to solve when you only have two particles that are interacting. So I have a proton, electron, you can imagine going around it if you like. As soon as I put two electrons in there, nothing works anymore. Like basically the math gets too difficult to solve. So it's kind of a fundamental limitation in what physicists know how to do, is that we know how to solve problems with two particles. 3 particles is like way too hard.
Yeah.
As soon as you get to 3, everything breaks loose and nothing works anymore. But that being said, there are models that do a decent job describing it, but you just can't get the exact solution. You can get very, very good approximations. So despite the Bohr's model success, ultimately it was wrong. And despite successes, Bohr model is incorrect. Because the Bohr model fundamentally was never going to be able to work for two electron atoms. And the reason is pretty clear if you think of the electron as really having wave-like properties. Because Bohr's model is only a wave around the circumference. It only has wave properties around the circumference of the orbital. However, if the electron's a wave, it has to be a wave in 3 dimensions, not just around the circumference. The electron has wave properties in 3 dimensions. So we have to come up with a model that predicted the wave shape in really 3 dimensions. And that's what Schrödinger found a way to do. He came up with Schrödinger in the 1920s, I think it was, came up with an equation that described how matter waves would work in 3 dimensions. So I'm going to write, now this is a differential equation, so if you have not had differential equations, this is going to look a little unfamiliar. We will not have to solve this equation. I just want to show you what it looks like so that you know where what we're about to do is coming from. So there was a big meeting in, let's say, 1927, if I'm remembering correctly, trying to figure out what the real nature of matter was. Trying to figure out, all right, well, we've got this wave interpretation, particle interpretation, what's really going on here? And it was like the all-star game of like best scientists ever. Because Einstein was there, Niels Bohr was there, Curie was there, Schrödinger was there. There's like a big picture where it's like every famous physicist of the 20th century is in this one photo. All the ones that were alive at the time. And one of these guys was Schrödinger. Schrödinger of the Schrödinger's cat fame. And his model works not just for atoms, but for all quantum particles, at least to a very high approximation. And he wanted to know what's the probability of finding the particle in different spots. So we know it's a wave. And I know when I measure the wave collapses into a particle. Well, what's the probability of finding the particle in different spots of the wave? So we'll say, what's the probability of finding particle different points of wave? And to do that, he had this wave function that he came up with. It was a function, again, it was in 3 dimensions, because quantum waves are going to be 3-dimensional waves. Call this the wave function, which you could imagine is looking like some wave, but in 3 dimensions. And this, he said, was proportional to whatever that wave function was squared. So you have this wave function. Something, we don't know what it is. We don't know why it works this way. But we know we can write down a function that when we square it, gives us the probability of finding the electron in different places. And to determine what this wave function is, he came up with this equation. Like all quantum mechanics things, it had Planck's constant in it. By 2 times the mass of the particle that we're working with. Nabla squared, I'll tell you what that is in just a sec. Times the wave function. Plus, this is the potential energy. So in this case, it would just be, for the atom, it would just be the electrostatic attraction between the 2 charges. Plus the electrostatic energy times the wave function has to equal the energy times the wave function. Now you might think, just looking at this equation, well, can't I just cancel the psi out? The psi being the wave function, the Greek letter psi. This is the total energy. It turns out that all of this funniness up here is just the kinetic energy of the particle. That Nabla squared, I'm going to write this down. People who are math majors will know what this means. So Nick, this is for you. It's basically a bunch of partial derivatives. People who are not math majors do not have to worry about that. But like I said, I want you to know where this comes from. Basically what you're doing is you are solving a really big calculus equation. And when you do that, you get the shapes of the atomic orbitals. So, how many of you guys took chemistry here again? Okay, all of them. Okay, good, excellent. Do you remember in chemistry making atomic orbitals that, or at least seeing atomic orbitals in your book that look like this? And then they get kind of more complicated the higher you guys all remember seeing those? Those 3-dimensional shapes are this. It's the solution to that equation. So what Schrödinger, by solving this equation, basically gave you a roadmap to figuring out all of chemistry. Kind of, right? If you can solve this equation, you can figure out the answer to how any 2 chemicals are going to react. The problem is that the math on this is ridiculously complicated and nobody can do that. At least not without the aid of very, very smart computers. But I want to go through the, not the math of this, but kind of the results of the math of this. Because with this, you can figure out the shape of the atomic orbitals. And from that, you can actually figure out why the periodic table has that screwy shape. The periodic table, the shape of the periodic table comes out of that equation. So I want to do that now and kind of tell you what the math predicts. Because it does a very good job of predicting what atoms should be there. And in fact, you can predict, using that, you can predict atoms that were missing in the periodic table. Just by looking at the wave functions you should have gotten out. They were actually able to find out a few missing atoms that they had not discovered, and then later people do some experiments and you're like, oh, this atom really does exist. First thing, we had this quantum number n. We're going to call it the principal quantum number because we're going to get it used. And that came because we said we have to match the wave on the boundary, so that we could only have certain wavelengths. Therefore, we could only have certain energies. We could count what those energies were. So quantization comes from matching up the wave on the boundaries. Matching up the wave on the boundaries. So, Bohr's model said, that's good. That's bad. The wave has to match up on the boundaries. This doesn't match up. This is bad. Well, that was only a boundary around a circle. It's the boundary around the orbit. And this is hard to visualize, but really you need to match up boundaries in 3 dimensions. So what's going to happen is that we are going to need, to match up 3 boundaries because we have 3 dimensions. Match 3 boundaries. Because we have 3 dimensions. Again, this just falls out of the math. It's not really just a wave around a circle, it's a wave kind of going throughout 3-dimensional space. It's like a sound wave, you can imagine it being, where the sound is coming out in all 3 dimensions at once. And that means that we need to have 3 quantum numbers. So I want to write down what those 3 quantum numbers are. One Bohr got right, the other 2 Bohr missed. So we're going to make a little table here. This is something you've probably seen in chemistry before, but if not, it doesn't matter, because we're going to go over it now. We already talked about n, that was the principal quantum. And that gave us the energy. Minus 13.6 electron volts divided by n squared. And we said n could be any positive integer. 1, 2, 3, etc. That's one quantum number we have to match up. There's another one. Another one that we call L. That's called the orbital angular momentum quantum number. If this one gives you the energy, this one gives you the shape of the orbital. So you had in chemistry class, you had a different way of labeling the shapes. What did you label the different shapes of orbitals? Anybody remember? Letters? S, P, D, and F. So the chemistry way of saying this is S, P, D, and F. The physicist way of saying this is just we label it with numbers. It turns out the shape is related to the total angular momentum. So this is your angular momentum curve. And the angular momentum, you can calculate it, is going to be L times L plus 1. Times again, Planck's constant, h bar. The L's can take certain, did you guys do the L notation in, you know what the L numbers can be from chemistry? You seen that before? You might not have. Anyway, L can be, let me get myself. L can be 0, 1, all the way up to n minus 1. So it can't go all the way up to n. So if n is 2, what's the biggest L can be? 1. So that determines the shape. There's a third quantum number. which we call M. Sometimes you hear this one called the magnetic quantum number.
So L can be any number up to n minus 1. It doesn't have to be n minus 1.
It does not have to be n minus 1. It can be any number. So if n is 3, what values can L have?
0
0,
and 1.
1, and 2. It can't be 3, but it can be any number that's smaller than n.
And it can be multiple ones too.
Yes. Yeah, we'll show that in a minute. So the way you get the periodic table is by going through all of the different possible combinations of these numbers. N is the magnetic quantum number. It turns out that if you turn on a magnetic field, so if I put my atom in a magnetic field, we showed the atomic lamp before, you saw the different lines of color. Turns out if you put your atom in a magnetic field, you get more lines of color. The lines start to split up into different lines. And the reason is that we change the energies of the different orbital shapes. So for example, I can split the different P's, D's, and F orbitals up so that they all have different energies. Whereas before, if I had a given n, they had all the same energy. So your magnetic quantum number is given by this m. Actually, it's usually written m sub L. And physics-wise, it correlates to not the angular momentum, but how much angular momentum you have going around the z-axis. So we call it LZ. LZ is given by m sub L h bar. And m sub L can be any number from negative L all the way up to positive L. So if L were 1, what values could m sub L be? Negative 1, 0, 1. So these are the 3 quantum numbers you get from Schrodinger's equation. Yeah?
Is the magnetic one also known as the spin?
It is not. There is a 4th one known as spin. I'm glad, and you led me right into what I wanted to talk about next. So it turns out this is not all the information, quite all the information, because we also have to worry about the spin of the electron. Now you might ask, well, what does it mean for a particle that is a wave to be spinning? That gets a little bit dicier, but it turns out the spin also has its own boundary conditions it has to match up with. So we have this the 4th quantum number, which we'll call ms, m sub s. This tells us how the electron is spinning. And it turns out there's really only 2 ways for the electron to spin. It can spin this way, or clockwise or counterclockwise. So we can write down the spin variable as being plus or minus 1/2 h bar. It tells us how much the electron is spinning, basically tells us what its angular momentum is from spinning. And m sub s numerically can be plus or minus 1/2. Now, with these quantum numbers, and with one more principle, we can predict the shape of the periodic table. So we have 4 quantum numbers. We also need this one more principle. The last principle we need is the Pauli exclusion principle. The Pauli exclusion principle is, for our purposes, it's pretty simple. It just says that no 2 electrons can be in the same state. two electrons can be in the same state. By same state, I simply mean they can't have the same quantum numbers.
Can I have like one of them be the same?
Yes, so they can have, I can have, n is 1, L is 0, so I can have 1, 0, 0, 1 half. 1, 0, 0, 1 half. That's fine. And then I can have another electron in 1, 0, 0, minus a half, because that, they're just different by 1 quantum number. They can't have all the same quantum numbers.
So it can be any of the quantum numbers, it's different.
Anyone's different, then you can put 2 electrons there. So you can have the same n, you can have the same L, you can even have the same m sub L, as long as one of the quantum numbers is different. It'll be fine. So let's see if we can predict the shape of the periodic table with this. How many elements are in the first row of the periodic table? 2. First row, 2 elements. Those 2 elements are hydrogen and helium. All right, well, let's look at our first energy level. N equals 1. We're going to write down N, L, M sub L, and M sub S. Start off with N is 1. If N is 1, what can L be?
0.
Only number can be a 0. What can M sub L be?
0.
So L has to be less than N, so L has to be 0. M sub L can be from negative L to positive L, so it also has to be 0, because negative L and positive L are both 0. What can M sub S be? Plus or minus a half. So you get this. Or it could be minus a half. So in the first energy level, I can fit, I have 2 states that I can put electrons, which means my first 2 atoms in the periodic table are going to be in that lowest energy level. Yeah?
Do you know which one between hydrogen and helium has like, the different spin?
Well, so hydrogen can be in either of these states. You can have an electron in here or an electron in here. And it doesn't matter which. You can measure it if you choose to, but it flips back. Hydrogen doesn't care. The 2 states are the same as far as hydrogen is. Helium will put 1 electron in, its first electron in one of the states, and then it will put its next electron in one of the other states. Okay, so it'll have electrons in both of these 2 states. So the last, we could say, let's just say arbitrarily that the hydrogen puts its first electron in here. Let's say helium also puts its first electron in the plus 1/2 state. Then the next electron would have to go into the minus 1/2 state. Why can't it also go into the plus 1/2 state? Because the exclusion principle says we can't put 2 electrons in the same state. So that's our first, this is our first energy level. It's our first row in the periodic table. How many elements do we have in the second row? 8 elements. Second row, 8 elements. So those 8 elements are lithium, if I remember it correctly, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. All right, well, let's see what quantum numbers we've had. We've already used up, so basically we're just going to keep adding electrons and see where they go. So we've already put electrons into these 2 states. So I'm filled, my first energy level is just filled. First, this would be your 1s orbital, completely filled. What's the next value of n that we can have? 2. What's the lowest value L that we could have for n equals 2? 0. What's the lowest value m sub L we could have?
0. Oh,
Wait. Negative 1. And then we'll say plus a half here. What else? What other? All right, so I'm going to say plus or minus a half just so I don't have to write double the amount of work. So there's really 2 electron states here. All right, so that's 2 of my 8 electron states. Yeah, question?
Since we chose the L to be 0 here, doesn't M sub L also have to be 0?
No, because remember, m sub L can be. Oh, yes, sorry. No, you're absolutely right. Yeah. That's interesting. Yes, this should absolutely be 0. Thank you. That would have caused troubles in a minute. Yeah, so L is 0, m sub L has to be 0 because m sub L goes from minus L to L. Thank you. Right. But that will take care of the rest of the L equals 0 terms. What's the next value L can take? Now L can take. If L is 1, then what's the lowest m sub L we can have? Negative. And again, spin is plus or minus a half. What's the next biggest m sub L we can have? Again, you get plus or minus a half for that state. That's still 2. That's still 2. That's still 5. Any other m sub L's I can have? Could have positive. Again, you get plus or minus a half. That's still 1. That's still 2. How many electron states do I have here? 8. How many electron states do I have in the second round? Lithium, beryllium, that's 2. 6 more over there, 8. So what we can correlate with this is that if I look at a particular L is 0. Here L is also 0, but I get 2 of them because I have 2 spin states. For L is 0, if the last electron I put in is in an L equals 0 state, you get something in the S block. You get something in those first 2 columns. Because if L is 0, there's only 2 ways I can make that. Right? If L is 0, then m sub L would have to also be 0, and then I can have 2 spin states. So the first block of the periodic table, the S block, I know that's way too many. For the S block, that's just when L equals 0. Your last electron has 0 for your angular momentum quantum. What if L is 1? How many electron states do I have for L equals 1? 6. So if L is 1, I've got 2 from this one, 2 from this one, 2 from this one. So that's a total of 6. If L is 1, then your shape is near your P block. That's for L equals 1. There we have 6. You might start to be detecting a pattern here. With 2, 6. If L is 2, how many electron states can I have for that value of L? So L is, let's go through. So L is 2. How many different m sub L's can I have? What different m sub L's can I have if L is 2? Negative 2. Negative 1. 0. 1. 2. So that's 5. But each of those has 2 spin states. So how many states do you have in total? 10. How many elements do you have run across the F block? or the D block? 10. So here, I'm not going to draw them all. This is your D block. L is 2 here. What would L be for your F block? So S block gets 0. T block gets 1, D block gets 2. L for the F block would have to be 3. How many M sub L values can you have for that F block? The D block would be 10, yep. Which if you look at your periodic table over here, and you count across, you get 10 elements. So all you're doing when you go up one number in the periodic table is you're adding one more, well, you're adding one more proton and one more electron. Which means you've got to add one more electron to this, to these energy shells. So you just have to go to whichever one's next. In this case, for L equals 3, I can have 7 values for M sub L. It would be -3, -2, -1, 0, 1, 2, and 3. That's 7 values. But for 2 spin states for each of those 7 values, how many elements should I have down in the F block? 14 going across. So F block is 14 elements. So what you can do, and what scientists did back in the day, originally they figured out the periodic table just looking at comparing the elements and seeing how they were similar and different, looking for trends, looking for things like atomic weight, electronegativity. But as people went further and further, every once in a while you'd go further down in the periodic table and there'd be something missing there. And so you'd say, all right, well, I'm pretty confident that the theory matches what we're finding in experiments. And something's missing over here. We don't know of any element, but there's got to be an element there because it matches the theory so very, very well. It'd be very shocking if the theory worked perfectly except for, oh, well, that one element doesn't exist. So what they did is people actually would go to particle accelerators and do various nuclear chemistry bits to try to make elements that were missing. And they had pretty good success in it. That's how a large percentage of the F block elements ended up turning up and how they were discovered. And basically people just made them in a lab because they could theorize based on the patterns that they were seeing that there had to be an element there that was missing. So, by the way, this is quantum mechanics. It's incredibly useful for figuring out fundamentally how chemistry works, and not just chemistry, but how physics works at a very fundamental level. I'm going to stop here for a second and take questions. So questions on the 4 quantum numbers that we have. No questions? Okay, in that case, I am going to need a volunteer. Nobody is a volunteer. I should probably tell you what you're going to do before I ask for volunteers. Basically, yes, good job, out the window. No, it's first floor, it's fine. Basically, we need to do course evaluations because we haven't done those yet. So I have brought up computers so that you can do that here. You can do it on, I believe you can do it on your smartphone if you've got internet access. So what I will do, I'm going to turn off the camera. I'm going to have you guys either take out your smartphone or you can grab one of the lab computers and do it on there. I have to leave the room for this, but I still need to bring the computers back. So the volunteer I need is just to come get me so that I know when they come in and bring the computers downstairs. Yeah, okay, thanks, Marissa. So let me just turn this off and then you guys can get started. I will just be